I think we all kind of grew up with this understanding that the sun have an expiration date, right?
Mm.
And astrophysicists have it meticulously mapped out.
Right, yeah. Like, we know exactly how much time is left.
Exactly. We think we know exactly how our solar system's ultimate battery works, and more importantly, exactly how much time we have left on the clock. But what if we've been reading that clock completely wrong?
Which is a pretty terrifying but also fascinating thought.
It really is.
Yeah.
Like, what if there is this massive invisible force churning inside our star right now that is actively manipulating how much time we actually have? So welcome to the deep dive. Today, we are exploring a really fascinating May 2026 article published in Astronomy and Astrophysics by an author named Adrian.
Yeah, and the core premise here is just going to challenge the foundational math we use to calculate the lifespan of our very own sun.
Okay, let's unpack this.
Yeah.
I want you to imagine taking the battery out of a familiar device, right? But then you realize that the chemical reactions inside aren't just burning down steadily.
You're doing something else entirely.
Right. Instead, they're being actively manipulated by a hidden magnetic current that nobody even knew was there. And that is essentially what astronomers are starting to realize about the stars in our universe.
Yeah, and it fundamentally shifts our understanding of stellar mechanics. I mean, scientists have recently discovered traces of what they call fossil magnetization on the corpses of dead stars.
Dead stars, meaning white dwarfs.
Exactly, on white dwarfs. And finding a magnetic field on a stellar remnant isn't just, an esoteric piece of trivia. It is a massive structural clue.
Like it changes the whole picture.
It really does. It has a direct ripple effect on how we calculate the lifespan of the sun. And by extension, our understanding of how stars age, how they bear fuel, and eventually die across the entire galaxy.
So discovering these magnetic fossils basically means we've been missing a major piece of the physics regarding how stars transition from one phase of their life cycle to the next.
Precisely. We've been missing a huge part of the puzzle.
Okay, so to understand the significance of a magnetic fossil, I feel like we do have to look at the violent life cycle that produces it, right?
Yeah, we have to start at the baseline, normal, to get why this is an anomaly.
Right. So we all know the standard progression for a star like ours. It spends billions of years just burning hydrogen, fusing it away.
And eventually that fuel runs out, the internal pressure drops, and the core collapses under its own immense gravity. Meanwhile, the outer layers swell massively, turning the star into a red giant.
And that transition creates an incredible internal extreme. The source material actually highlights this brilliant visual representation provided by Paul G. Beck from KU Leuven.
Oh, yeah, that image is incredible.
It really perfectly illustrates this duality. It shows this intensely hot, unbelievably dense core just waiting there, buried deep inside the massively bloated, swollen outer layers of the red giant.
It's like a puffed up hot air balloon, right?
That's a good way to look at it.
Where it just burns away all its fabric and all you have left is the blazing hot burner behind. Exactly, because eventually, as the star continues to age, those swollen outer layers disperse entirely into the vacuum of space. The only thing left behind is that compact, scorching core.
Which is the white dwarf.
Right. That leftover ember is the white dwarf.
Okay, so the outer envelope is gone, leaving just the core. But I'm kind of hung up on the sheer mechanical violence of that transition.
It is incredibly violent, yes.
Right, because you have a star collapsing, ballooning to a massive size, and then just violently shedding its outer plasma layers into space. So given the scale of that trauma, how could something as seemingly delicate as a magnetic field survive that violent shedding process to become a fossil on the remaining white dwarf?
Well, this raises an important question, and to answer it, we have to look at how we gather this data in the first place.
Because we can't just send a probe in there.
Right. You can't just X-ray a red giant that is trillions of miles away to see its internal magnetic structure, nor can you drop a probe into its core. So astronomers rely on a methodology called astroseismology.
Astroseismology.
Yeah. It operates on the same principles as terrestrial seismology, where, scientists study how seismic waves from earthquakes travel through the ground to map out the Earth's internal layers.
So in astroseismology, astronomers are literally measuring starquakes.
Exactly. They're measuring the internal oscillations of the stars.
I know astroseismology has been a massive game changer for astronomy, but what is actually causing a star to quake in the first place?
It really comes down to fluid dynamics. The outer layers of stars, like red giants, they are incredibly turbulent.
Just boiling, right?
Yeah, they're essentially boiling convective oceans of plasma. And that violent churning constantly generates massive acoustic waves.
Sound waves.
Right, sound waves. And these acoustic waves plunge downward into the deep interior of the star. But when they hit the incredibly dense, collapsed core, the sudden change in density forces the waves to refract.
They bounce back up.
Exactly, they bounce back up toward the surface. So, by observing the minute changes in the starlight, scientists can detect the surface of the star expanding and contracting as these waves hit it.
Oh, wow.
And because those acoustic waves physically traveled through the star's deep interior, their frequency carries the structural signature of everything they pass through.
Okay, here's where it gets really interesting for me, because I was thinking about this acoustic refraction, and it's practically identical to trying to hang a heavy shelf in your living room.
What do you mean?
Well, you need to find a wooden stud behind the drywall, right? But you can't see through the wall, so you knock on it.
I see where you're going with this.
Right, you tap the drywall, and you listen to how the sound wave behaves. When it sounds hollow, you know it's empty space. But when the pitch suddenly changes and sounds solid, the wave is refracted off the dense wood.
Yeah, you've mapped the invisible anatomy of your house using sound.
Exactly. And scientists are doing the exact same thing, just listening to the frequency shifts of a giant ball of plasma light years away.
That stud finder concept is exactly what's happening, and the underlying physics are pretty much identical. But when astronomers use this technique to map out these aging stars, the pitch they heard revealed a massive glaring contradiction in the data.
What kind of contradiction?
Well, astroseismology showed that red giants, the big bloated stars, have incredibly strong magnetic fields trapped deep inside their dense cores.
Okay.
However, when they looked at white dwarfs, which again are just the leftover cores of dead red giants, they found something completely different. The white dwarfs exhibited magnetic fields on their surface.
Wait, that breaks the structural logic.
Right.
Yeah, I mean, if the white dwarf is literally just the old red giant's core with the outer layer stripped away, the magnetism shouldn't just pack its bags and relocate from the deep interior of the core to the surface of the core.
No, it certainly didn't literally teleport.
So our map of the red giant's interior must have been fundamentally wrong from the start, right? The field had to already be there in those outer layers, and our previous models just couldn't account for it.
Precisely. And that contradiction forced researchers to build an entirely new model, because the old paradigm that the magnetic field was just this tight, static ball of energy confined to the center of the core that was clearly flawed.
So what did they come up with?
They developed what they are calling the fossil field model. The real breakthrough was understanding the physical mechanics of the collapsing star. The magnetic field doesn't just sit statically inside the core, it actively reorganizes itself as the star evolves.
Reorganizes. What are the actual physics of that reorganization? Like, how does a magnetic field just change its shape inside a star?
Well, it goes back to how plasma and magnetic fields interact. In a star, the magnetic field is effectively baked into the plasma. They are coupled together.
Okay, they're linked.
Right. And as the star ages and its core runs out of hydrogen, it collapses inward under its own weight. The plasma compresses dramatically.
But the magnetic field can't be compressed.
Exactly. The magnetic field lines cannot simply be crushed out of existence. So as the core squeezes down, it forces the magnetic energy to buckle. The field seeks the path of least resistance, pushing outward into the surrounding, less dense layers of the star.
Okay, that makes perfect sense. It's kind of like squeezing a water balloon.
Yeah, that's a perfect analogy.
Right, because when you apply immense pressure to the center of the balloon, the water doesn't just vanish. It's forced outward, bulging into the outer edges where there's less resistance.
Exactly.
So as the core collapses, the magnetic energy gets squeezed out of the deep center and bulges into the outer layers.
That fluid dynamic is highly accurate. And to visualize this, the source material actually details these really complex computer simulations run by Lucas Einrumhoff.
He's from the Institute of Science and Technology, Austria, right? ISTA.
Yes, from ISTA. He simulated how the compression of an aging star actively alters the topology of its magnetic field. And in his models, as the field is squeezed outward, it reorganizes into these concentric shells around the core.
Like layers in a jawbreaker candy.
Yeah, layered just like that. The research visualizes these shells as distinct pink lines curving outward through the interior of the star.
Pink shells, okay.
Right. And because of this structural reorganization, the magnetic field ends up being far stronger in those outer concentric shells than it is deep down in the absolute center of the core.
Oh, wow. Okay, so by the time the star reaches the end of its red giant phase and completely sheds its massive outer envelope, what we are left with is the white dwarf.
Exactly.
And the magnetic field we detect on the surface of that white dwarf is simply the fossilized remnant, the leftover pink shell, basically of the magnetic field that got squeezed outward during the red giant phase.
Yes, that's exactly it.
So the contradiction is entirely solved.
It resolves the data perfectly.
Right.
The surface field on the white dwarf is the literal fossil of that internal reorganization process.
Man, the mechanics of that are fascinating. But it does make me wonder about the scale and, like, the frequency of this phenomenon.
How common it is.
Yeah. Like, is this just an anomaly? Are there only a handful of strange stars out there squeezing their magnetic fields into these pink shells? Or is this happening systematically inside every dying star?
Well, what's fascinating here is that this hidden magnetic topology might actually be the universal standard.
Really?
Yeah. The source article provides a very telling quote from Lucas Einrumhoff regarding their findings. He states, and I quote, "We cannot always detect this magnetism, but our work indicates that most stars are probably magnetic."
Most stars.
The vast majority.
That's incredible. Why hasn't this been common knowledge before now?
It's simply a limitation of our instruments.
Yeah.
I mean, these fields are incredibly difficult to detect when they are buried beneath millions of miles of boiling plasma.
Oh, sure. That makes sense.
But these astroseismic models strongly suggest that hidden reorganizing magnetism is the rule across the cosmos, not the exception.
Okay, so what does this all mean? If most stars possess these hidden reorganizing magnetic structures, we really have to bring the lens back home.
Back to our own sun.
Right, back to the mission statement we started with regarding the expiration date of our sun. Can you connect the underlying physics of these distant magnetic shells inside dying stars to the reality of our own solar system? Like, how does this actually alter the lifespan of our sun?
Well, the implication is massive. Right now, despite all our observational technology, astronomers have a significant blind spot. We do not know if the core of our sun is magnetic.
Wait, really? We don't know that.
We observe the surface, of course. We track solar flares, coronal mass ejection, surface magnetic storms, all of that. But the deep, dense fusion core remains an observational mystery.
I had no idea that was still a mystery.
It is. However, if the core of our sun is magnetic, as these new fossil models suggest most stars are, it completely changes the timeline of our solar system.
Because of the reorganization.
Because a strong reorganizing magnetic field deep inside a star acts as a powerful mixing mechanism.
A mixing mechanism.
Yeah.
How exactly does a magnetic field mix the interior of a star?
Think about the field distribution. A star fuses hydrogen into helium strictly within its incredibly hot, dense core. But there is a massive reservoir of fresh, unburnt hydrogen sitting out in the outer layers.
The radiative and convective zones.
Exactly. Normally, the core cannot access that outer fuel. It's just sitting there. However, magnetic fields moving through plasma create instabilities. They generate turbulence.
Okay.
So if there is a reorganizing magnetic field inside the sun, that turbulence physically churns the plasma. It pulls that fresh, unburnt hydrogen from the outer layers down into the core, actively feeding the nuclear reactor.
Oh, man. That sounds exactly like what happens when a lawnmower engine starts to sputter, because the gas tank is almost empty.
How so?
Well, the fuel sitting at the very edges of the tank isn't naturally flowing down into the fuel line, right? So you grab the handle and you vigorously shake the lawnmower.
Oh, right.
You slosh the tank to force those last few pockets of unburnt fuel down into the engine to keep it running for just a little while longer. This unseen magnetic field is essentially shaking the sun's gas tank.
That's a great way to picture it.
It's pulling fresh hydrogen down to fuel the fusion process and effectively prolong the life of the star.
That physical mixing could significantly prolong the star's life, yes. It could mean our sun has a vastly longer lifespan than our current models predict, simply because those models never factored in the magnetic churning of the fuel supply.
Okay, but sticking strictly to the source material here, I do want to push back a little on the idea that this is inherently good news for the longevity of the solar system.
Fair enough.
Doesn't the physics of this mixing mechanism mean it could also have the exact opposite effect? I mean, if you disrupt a delicately balanced fusion reactor, It might not just give you more time.
That is the double-edged sword of this discovery, and the source is explicit about it. While a magnetic field could churn fresh hydrogen into the core and prolong the star's life, it could also critically disrupt the internal hydrodynamics.
So it could break the process.
Right. Depending on the exact geometry of that field, how intensely those magnetic shells form and press against the surrounding plasma, it could alter the internal pressure.
In a bad way.
It could suppress convection in certain areas or change how heat radiates outward. And in that scenario, the magnetic mixing might actually throttle the fusion process.
And shrinking the lifespan.
Exactly, potentially shortening the sun's life compared to our baseline estimates.
So, returning to the lawnmower analogy, the magnetic turbulence could be feeding the engine extra gas, or it could be flooding the engine and stalling it out entirely.
That is exactly the situation we are in.
And right now, we just don't know which reality we're living in. Now, to be clear to anyone listening, the sun is not going to burn out tomorrow. We are still talking about timelines spanning billions of years.
Oh, absolutely. This won't happen in our lifetimes.
Right. But it fundamentally breaks the math we use to understand the very ground we are standing on.
It proves our baseline mathematical models are incomplete. The ultimate goal of this astroseismology research of studying these magnetic fossils on dead white dwarfs is to refine our physical models well enough so that we can finally decipher the seismic waves of our own sun.
We need to build a better stud finder for our own star.
Exactly. Only then will we know for sure what kind of magnetic topology is hiding deep inside our star and whether it is extending our timeline or cutting it short.
Wow. Let's quickly recap the journey we just took, because the chain of discovery here is truly remarkable. We started by looking at how a star exhausts its hydrogen, collapses its core, swells into a red giant, and eventually sheds its outer layers to leave behind a white dwarf.
Right, the basic life cycle.
And we learned that astronomers use astroseismology, measuring acoustic waves that refract off the dense core, to map the invisible interiors of these stars. That technique revealed a contradiction where the core's magnetism seemed to miraculously appear on the surface of the white dwarf.
Which led to the fossil field model.
Exactly. This forced astrophysicists to realize that a collapsing core actively squeezes its magnetic field, forcing it to buckle outward into those concentric pink shells. And finding these magnetic fossils on dead stars proves that hidden magnetism is likely the rule for most stars.
Most stars, yeah.
Meaning our own sun might currently have a magnetic mixer churning its fuel supply, completely altering our calculations of its lifespan.
If we connect this to the bigger picture, it really serves as a profound reminder of why intellectual humility is necessary in science.
Yeah, we think we know everything.
We do. We often treat foundational measurements like the estimated lifespan of our sun as fixed, absolute facts. But science is a continuous process of refinement. When new methodologies, like astroseismology, allow us to observe previously invisible realms, we must be willing to rebuild our models from the ground up.
The data dictates the reality, not our historical assumptions. And I want to leave you with a final thought to mull over, building directly on the implications we've unpacked today. Consider Lucas Einarmhoff's statement that most stars are probably magnetic. If that is true, and this unseen magnetic turbulence can drastically alter how quickly a star burns its fuel, either extending its life or shortening it. What does that mean for our understanding of the entire universe?
That's a huge question.
Every time we look out into the cosmos, astrophysicists estimate the age and evolution of the universe based on how long we think stars live. We use stellar lifespans, the ultimate cosmic clock, to measure deep time.
Right, they are our baseline.
But if all those stars have hidden magnetic pendulums swinging inside them, actively altering the speed of those clocks, how many other absolute certainties about the age and structure of our universe are currently being manipulated by invisible forces we simply haven't learned to detect yet?
It is a staggering question that challenges the very foundation of astrophysics.
It really is. Thank you for joining us on this deep dive. Keep questioning the consensus and keep looking up.